All right, we are focusing on waves today. We've got three types of waves in physics. We've got mechanical waves, electromagnetic waves, and matter waves. Chapter 16, we're going to focus on mechanical waves, but that's going to give us a nice foundation. The basic principles of waves remain the same. And later in the semester, we're going to focus in on electromagnetic waves, which essentially light, and that's going to allow us to talk about some interesting phenomena associated with light. But for today, we're focusing on mechanical. So for mechanical waves, we've got waves that are governed by Newton's laws. All right, so remember back to 101, mechanical waves are governed by Newton's laws, and mechanical waves also require a medium to exist. Right, when you talk about a water wave only exists because there's water. Sound wave requires a medium to travel through. Think about at your favorite stadium, watching your favorite team. For there to be a fan wave, you need fans. So that's one specific thing to mechanical waves. It turns out electromagnetic waves do not require a medium, and that's one of many interesting aspects of electromagnetic waves. All right, so mechanical waves, I've got this figure from the book here that is going to allow us to talk about some of the basic properties of waves, and so we're going to just jump right in here. And the first thing we're going to mention about a wave is that a wave has a period. A wave is this repeating pattern or form. The period is the time for one complete oscillation of that form or shape. And the unit for the period is a second. Frequency is related to the period. Frequency is 1 over the period. And the frequency is the number of oscillations per unit time, or number of oscillations per second. The unit for frequency is inverse seconds, or hertz. The next thing up, basic characteristic of a wave, is the wavelength. This is quite literally the length of the wave. We use the symbol lambda to represent a wavelength, and the wavelength is measured in typical units of meters or centimeters or kilometers. And again, if you look at this picture here, you can obviously see the wavelength is literally just the length that the wave takes. The next thing that we want to mention is the amplitude. So the amplitude, you can think of it as the height of the wave. It's the maximum displacement from equilibrium. So if you look at the picture here, it's nicely shown. The amplitude is in units of meters as well. And then the last thing that we want to mention is the speed of a wave. The speed of a wave is connected to the wavelength and the frequency. So the product of the wavelength and the frequency of the wave gives you the speed of the wave. Since frequency is 1 over the period, you could also take wavelength divided by the period, and that also gives you the speed of the wave. And so the speed of any given wave essentially depends on the material or the medium in which it's propagating through. Now we've got two types of mechanical waves. We've got transverse waves, where the disturbance, the wave, the shape, disturbance is perpendicular to propagation. And we have longitudinal waves, where the disturbance is parallel to the propagation. And the easiest way to see this is in this nice figure from the book. We've got the disturbance going up and down in this first picture, but the wave is traveling to the right. Whereas for the longitudinal wave, we have the disturbance essentially going back and forth, right to left, and the wave itself is traveling to the right. So two different types of waves, where the propagation is either, where the disturbance is either perpendicular or parallel to the propagation. All right, so in this example, we have a wave drawn on an x and y coordinate system. We're given that the speed of the wave is 10 meters per second to the right, and we're asked to find some of the basic properties of the wave: the wavelength, the frequency, the amplitude, and the period. All right, so we're going to start out solving for the wavelength, finding the wavelength. So let's just begin here. So first up is the wavelength. Now, to find the wavelength, what I can use here is the actual picture itself. Remember, the wavelength is the literal length of the wave, so all I have to do here is sketch out one complete wave, and it doesn't actually matter where I start sketching out. You can see here I've traced out one complete oscillation of the wave, and I get 4 meters. Notice that if I choose a different portion of the wave, like starting right here, and sketch out the full pattern until it repeats, I actually get the exact same result. In both of these cases, the wavelength is 4 meters. All right. Now, next up is the frequency. So let's find the frequency of the wave. Now, how are we going to do that? Well, we're going to do that by taking advantage of the relationship between the wavelength, the frequency, and the speed. And so using that expression, we can calculate the frequency just by taking the ratio of the speed and the wavelength. So the speed is 10 meters per second. The wavelength is 4 meters. That makes the frequency 2.5 inverse seconds, or 2.5 hertz. All right. Now, next up, we have the amplitude. Now, the amplitude, just like the wavelength, I can get the amplitude directly out of the figure, and the way I can get that is by noticing the maximum displacement, either above or below. Doesn't matter where I do this. All of those blue lines have a length of 5 meters, whether it's above or below that equilibrium position, and so the amplitude of this wave is 5 meters. And then the last thing that I want to find is the period of the wave. And it turns out, since I already have the frequency, all right, trying to make a square, not happening. Since I already have the frequency, then I can get the period by looking at 1 over the frequency. And so the frequency is 2.5 inverse seconds. So that makes the period 1 over 2.5 seconds. And that is going to be 0.4 seconds. All right, and there we have it. Just given a sketch of a wave, determining the basic properties of the wave. All right, now that we know the basics of waves, we need to go over how to model a wave or how to represent a wave mathematically. We're going to start with this figure from the textbook where on the left, here I've got a device connected to a rope, and this device is free to oscillate above and below this equilibrium position by an amount A. Right? Now, the top portion of the figure shows the rope after this device has oscillated through one full period of oscillation. And so you can see that there is one full wave on the rope. And so as we go down this figure, time is increasing. Each figure represents a time step of 1/8 of the period. So once we get to the bottom, going through 8 intervals, we'll have gone through another period of the wave. So if we focus on this portion of the rope that's connected to the oscillator, we can watch as time goes on what happens to the position of that piece of the rope. Now, initially, that piece goes up. It goes up to some maximum height plus A. Then it starts coming back down, goes back through its initial position, goes down all the way to the maximum displacement below where it started, and then it goes back up and then ends exactly where it started. And you can see that at the end, if you look at the rope, you have 2 full waves now on the rope, because that device was able to oscillate through another full period of the wave. Now, the reason I like this figure is that it allows us to make the connection between the x position on the rope and the wavelength. So as that device oscillates, the shape on the rope increases until you get a length of lambda, the wavelength, and then you have a full wave on the rope. And then that device oscillates for another amount of time equal to the full period, and you have another full wavelength on the rope. And so the way that we are going to model this mathematically is with the sine function. So if you look at that shape, that reminds us of the sine function, and remember that the sine function takes an argument, an angle, and that angle can start at 0 and increase to 2 pi radian, and then after you get past 2 pi radian, the sine curve repeats, right? So very similar to what we're looking at in the figure above. And so we can take those two relationships that for the sine function, theta can go through 2 pi, and the position here can go all the way up to the wavelength, and we can write down this relationship where we take the ratio of those two expressions. And then if we rearrange that, then we can write out an expression for theta in terms of the position. And again, the reason we're doing this is we want to write out a mathematical model, a function that represents this shape, this wave. And so if we plug in for theta, we can write out a simple function, just the sine function. Out in front of the sine function is the amplitude, right? That'll tell us the maximum displacement. And then instead of theta, I'm plugging in 2 pi over lambda times x. Now, of course, the shape or the wave in our rope was actually changing with time. And so if we want to take that into account, we need to include some time dependence in our wave function. And so if our wave, and in this case was traveling in the plus x direction at constant speed, then the way we incorporate the time dependence is by including a minus bt term in the sine argument. Now, that allows us to write y not just as a function of x, but now it's a function of x and t. And so then we're going to do a little bit of algebra. We're going to distribute the 2 pi over lambda. And then we're going to simplify the expression by introducing one new term and reintroducing a term we've seen in 101. The new term is known as the wave number, which we define as k, which equals 2 pi over lambda. So we're going to swap out 2 pi over lambda for k. The units for the wave number are inverse meters. And then the term that we've seen before is omega. That's the angular frequency. And omega is 2 pi over the period. And so if we multiply and divide by lambda, we can essentially write omega as 2 pi over lambda multiplied by the speed. And so we're going to substitute out for both of these terms with our new expressions k and omega. So that allows us to write out that wave function as kx minus omega t. Now you'll notice that I have a plus and a minus term here. That's just a shorthand to write out two different functions with only one expression. So the minus you would use if your wave was traveling in the plus x direction, and the plus you would use if it was traveling in the minus x direction. Something to note, the speed of the wave, which we've written in terms of lambda and frequency and period, well, we can also write it in terms of angular frequency and wave number, and so the speed is omega over k. The last thing that we can do is we can introduce an arbitrary phase angle, that's this plus phi term. We can introduce that to have the most general form of our function, which we're referring to as our wave function. So this is our mathematical representation, the most generic representation for the mechanical waves that we've been discussing. Okay, so the last thing that we want to go over is first a review from 101. Remember, if we have a position function, which back in kinematics in 101, the position was a function of time, then we could take the derivative of that function with respect to time to get the velocity, and then we could take the derivative of the velocity function with respect to time to get the acceleration, right? And taking the derivative of velocity with respect to time is equivalent to taking two derivatives with respect to time of the position function. Now, our position function for our wave isn't simply a function of time, it's actually a function of position and time. And what this means is that if we want to get the velocity function, then we need to take a partial derivative rather than a regular derivative. A partial derivative because we have variables of x and t, and we only want to take the derivative with respect to t. In practice, what this means is that you essentially treat the x variable as a constant when you're taking the derivative. All right, so if you take the partial derivative of our position function, we get an expression that looks very similar to what we saw in chapter 15 during 101. This is the velocity of the medium as the wave is propagating through. So this is the velocity at a specific location, say on the rope, at a specific time. All right, that's what this function represents. Now, if you take the partial derivative of this velocity function, then you get the acceleration function. Now, again, this is the acceleration of a piece of the medium, right? So at a specific position, at a specific time, what is the acceleration of that piece of the medium, right? That's how you interpret these two expressions, the velocity and the acceleration. Now, the last thing that we want to mention about the wave expressions is that you can combine the position dependent function and the time dependent function in a way to end up with what's known as the linear wave equation. Now, I skipped the algebra. It's included in the textbook if you want to check it out. But the end result is what's known as the linear wave equation. And the linear wave equation is one of the most important relationships that we have in physics. And the truly amazing thing about it is that the position function, which is a function of, or this wave function, which is a function of position and time, if you take the derivative of that function with respect to position twice, and you take the derivative of that function with respect to time twice, you get nearly identical things. The only difference is that there's a factor out front. So there's 1 over the speed squared connects taking two derivatives of the function with respect to position and two derivatives of the function with respect to time. Right? So this is the linear wave equation. Now, the position function up here, that is a solution to the linear wave equation, right? So that is to say, if you were to plug in our expression for y, take two derivatives with respect to position, and then plugged in on the right-hand side and took two derivatives with respect to time, you would get the same thing multiplied by a 1 over v squared out front, right? It's incredible. Now, the last thing that we need to talk about is that the speed of a wave on a stretched spring, what it depends on. So a wave, the speed of a wave depends on the characteristics of the medium. And so what does that mean? Well, it can mean different things for different media, but what I want to focus on is a stretched spring. And so the thing that matters on a stretched spring is the linear mass density. So that is, if you take the mass of the string, the rope, and you divide it by the length of the rope, that quantity mu is what we care about, the linear mass density. So if your string is stretched at a constant tension, and remember, tension, the book represents as F sub t. If your string is under constant tension, then the speed of the wave along your string is going to be the square root of the tension divided by mu, divided by the linear mass density. All right, so we'll look at a few examples in class and over the next few days where the tension of the rope is given, the linear mass density is given, and then we need to determine the speed at which a wave would propagate through that medium. We will also look at some examples where we may be given the speed at which the wave is propagating and the linear mass density, and then need to determine what the tension of the rope needs to be. And so those are all coming up. That's it.